Hi, the lecture today is about a very important concept in calculus, and for that reason it's called the fundamental theorem of calculus. It is going to define essentially how you will deal with just about any calculus problem from now on. To explain it, I'll start by an example, go through some area calculation, and then come back and explain what the fundamental theorem of calculus is going to do for us in a context similar to the problem we are looking at. We are going to have a theorem that's going to tell us how to calculate any integral very quickly. Let's go ahead and take a look at this function. Let's consider y is equal to, say, I take a very simple problem, so we are not going to be stuck with too much side calculation, and then I ask, find the area under this function and over interval from 1 to x. So here's our function. We want to calculate the area. One way that this problem looks different from the previous problems we have looked at is that instead of giving an interval that starts and ends at some specific number, the endpoint of my interval itself is the variable x. So let's see how does that show itself on a picture. Suppose I have a coordinate system here. Let's go ahead and draw this function carefully. So suppose this is 1, 2, say 3, 4, and so on, and say 1, 2, 3, and so on. At 0 we are at 2. Then it's going to have a slope of 2 while it's going up. So I chose a straight line. Our life will be a bit easier. Question is, we want to find the area that's underneath this and extends over, starting at 1. Use a different color here. So here's our starting point 1 and some ending point on a specific ending point. Let's call it x. We want to find this area. Well, I chose this simple problem so that we can use our knowledge from high school and find the area quickly. How would our high school knowledge going to be helpful here? Well, you want to calculate the area of this region. This is the region you want to find out. It's really a trapezoid. If you remember from high school how to calculate the area of a trapezoid, you're done. If you don't remember that either, no problem. Let's go ahead, break this into two pieces. So down here I have a simple rectangle, and up here I have a triangle. two pieces. What is the area of this red piece? How do you calculate the area of a rectangle? You take the height of it, multiply it by the base of it. Well, what's the height? How tall is this? Well, if you take 1 and plug it in your function, remember this is y is equal to 2x plus 2. At 1, we are at 4. So this is the height of this thing is 4. So 4 times, how wide is it? I'm going from 1 to x. How do you find the width? That's just x minus 1. 4x minus 4. That would be the area for this piece. How about this one? That is a triangle. How do you calculate the area of a triangle? You multiply the base. Here's the base. X minus 1 again. Here's the base. Same base. X minus 1 is here also. How tall is this? Well, at the point x, the height of this function all the way up here is 2x plus 2. Plug x here, you get 2x plus 2. 2x plus 2 minus this height, 2x plus 2 minus this height, which is 4, gives us the height here. Now I have to multiply base and height, divide by 2. Let's simplify this. I write x plus x minus 1. The other one is 2x minus 2 divided by 2. If the calculation of this mystified you, let me repeat it in another style. Here this run is x minus 1. Slope is 2. Okay, so this run was x minus 1. Slope of this line is 2. So the height of this section from here to here, which is the rise, is going to be the run times the slope. Run is x minus 1. Slope is 2. So 2 times x minus 1 will be this. Okay, next layer. Let's go ahead, clean this up. This 2's here and the 2 here, I can cancel them out, and I'll have x minus 1 squared. So the total area that you have, this piece and that piece added to each other, I'll have 4x minus 4 contribution from the rectangle, x minus 1 squared contribution from the triangle. Let's just go clean this up. 4x minus 4, open this, x squared minus 2x plus 1, simplify x squared first. 4x minus 2x is just 2x, minus 4 plus 1 is just minus 3. So we found an area easily because it was reducible to items we know from high school, rectangles and triangles. If it was curved here, of course we would have had much harder time, but didn't want to waste time on those things. We have already done those type of problems. This is the area. So let's look at the roof of this area. What is the equation of the roof? What do I mean by roof? Roof is just, this is the roof. This is limiting the region. Well, equation of the roof is y is equal to 2x plus 2. Now look at these two closely. Look at this formula and this formula. Are they connected to each other in any way? All the stuff that you have learned in calculus so far, what do you see as a connection between this function and that function? Pause this thing for a minute. Just stare at them and see if you can discover the connection yourself. Okay? Are you ready? Well, a connection is rather obvious in this example if you take area of function and differentiate it, you are going to get the equation of the roof written in a non-professional way. If I take area and differentiate it with respect to the variable that indicate last wall of the region, if I take the area and differentiate it, I'll get the roof. Well, fundamental theorem of calculus has two portions. One of them is just to write this in a fancy style. That's all it says. Let's go ahead and repeat what we want to say. The theorem itself is going to sound rather cumbersome and has a new notation. It's going to throw you off some, but what is in it is not a very complicated concept. So if you have, let me draw this thing again. If you have any nice function, whatever, and you start calculating the area from some fixed location, let's call it A, and then you go as far as some variable location, we call it X. So think of this as a wall of a piston that can move to the right or left, just a moving wall. Now if you go ahead and calculate this area from starting point A to the moving point X, of course depends on where that X is at that moment. So area is a function of where you care to stop. It is a peculiar type of a function. You can call it area up to here. Area up to X is whatever it happens to be. We are saying that if you calculate the area up to this X, you get, of course, a function of X. If you differentiate it, you are going to get the formula of this roof or the curved side of this region. So area, if it is differentiated, is going to give you that function back. So fundamental theorem of calculus, sometimes they abbreviate it fundamental F, theorem T, calculus C, part 1. That is what it is going to say. That we are not going to let you off the hook that easy. We are going to make this complicated. First of all, what is that area? Area up to X. How did we use to do areas? We used to have this integral sign. Is that right? Now, integral sign, here's the problem. We are starting at A, and instead of fixed ending point, which we used to write as a B, now we are saying I want to stop at X. Inside, the integrand used to be a function f, and whatever variable you wanted to use for it would have been fine, except now you have to be careful that the dummy variable that you use here better not to collide with this x that you are designating to be the endpoint of your interval. So in order not to use the x to mean something else, we go ahead, choose whatever other letter we might like. Anything else would do. So here is customary notation, say f of t dt. What is this t referring to? This t is referring to breaking this up to various strips, and t is indicating where the strip is. So if you have a strip here, and t is more or less the location of the strip, f of t will be the height at that location, not to be confused with the x, which is some other variable now and indicates the endpoint of your region of integration. Now area of 2x, we could use a of x, for example. Let's call it a of x, just not to confuse you when you are reading your text. They like to use a letter related to that. Your book calls it g of x. I would have liked to call it just a of x. It makes more sense. Either way, if you call it a or you call it g, what the fundamental theorem says is that if you differentiate these guys, if you differentiate g, or in my choice, if I differentiate a, either way, I'm going to get the function f evaluated at whatever you are evaluating these functions at. It will be f of x. Let's see if we understood what this last formalism say. Okay, the concept here was easy. The derivative of area is the roof. But when it comes into this notation, well, all hell breaks loose, and the notation tends to overwhelm us. We have to go keep reminding ourselves what these things are, and then come back and then go ahead and do what we want to do. Here's an example. Suppose g of x is equal to integral from 1 to x of, say, sine of radical t dt. So I just pulled the function out of the hat here, and I hope it behaves right. I plug it here, and I'm integrating from 1 to x. What is this integral? Well, really, God knows, some complicated integral. All we care about here is that what's going to happen if I take a derivative of this function. You have to think that there was a region. This was the formula for the roof of it. We was calculating area from 1 to x, and that was the area. If I differentiate that area, I'm going to get the equation of the roof located at this point. So all it turns out to be, well, the roof is just the integrand, and the answer is sine of radical x. So among the calculus problems, perhaps this is the easiest one. You're really not doing anything. All that you do is that the integrand is written at this letter, at this location. So nothing else is happening at all. But the concept that is going through this is huge. It's much more than all the other algebra we do in all sorts of other problems. At any rate, just keep this in mind. If you understand it, that is grand. Next best thing is to just keep it in memory and practice it often enough until you just get the hang of it. Let's go ahead and do something else. Suppose I have h of x so h of x is some integral. That integral would not have been too disastrous to try to calculate, but we are not there yet, and we don't need the integral. If I want to calculate h prime of x, the derivative of this function is simply the integrand evaluated at this upper end of region of integration. That's all. Now, for the fundamental theorem of calculus part 2, there is another part to this whole interesting story. So, fundamental theorem of calculus part 2. Let me go ahead quickly draw that picture I had up there. This time I'm not going to be very careful about the dimensions. at something looking, not going to draw to scale so that it will fit here. So this was my function. Let me call it f of x 2x plus 2. That was the original roof. We had started calculating everything starting at 1. So this was 2. And we had found out that if I wish to stop at the location x, the area up to here, it was a total of, let me see if I remember, it was, after all this, it was x squared plus 2x minus 3. So if I decide to stop here, area is x squared plus 2x minus, I wish I had made a bit more room, minus 3. I can always move my x somewhere else here. From 1 to x, area is that. Now suppose I consider some point, say A, and some other point, let's color it differently, let's say B. Let's ask the following question: what is the area under that same function 2x plus 2 over interval from A to B? Well, what would be the area all the way up to A? Maybe I should let you to answer this question using that information and come back here instead of waiting for me to do it. I'm sure you can do it yourself. Okay, pause for a moment and come back and tell me, using this work that we have done, that the area from 1 to x is this formula. What would be the area from A to B? Okay, so you go and come back. I continue here. Say area from 1 up to A, the way I get it is that instead of using x, I put A. This was a moving wall. I bring that wall here to become A. In that case, x is just equal to A. Area up to A is A squared plus 2A minus 3. Area up to B, what is that? Now just move x over here. Remember, x could be any number. Now suppose x is just b. So area up to b means I am calculating, excuse me, I'm calculating all the way up to here. Well, all I have to do is just put b here, b squared plus 2b minus 3. Now area between A and B. Or sometimes say over A to B. Well, if that is the area I want, this is the area. From A to B, that is the area I want to calculate. What do I do with these two? Yes, you're right. Just subtract the two of them. I just write here b squared plus 2b minus 3 minus a squared plus 2a minus 3. Now let's we have the answer here. That's the area. the main question is, what role does the antiderivative of the function play here? Remember, we just saw a role for the antiderivative here. The derivative of area is the roof. It means area is an antiderivative of the roof. So let's write this. Area is an antiderivative of the root. Just the same way that the excuse me, but I guess it's the end of the day. Area is an antiderivative of the roof. Instead of saying roof is the derivative of the area, I can say area is an antiderivative of the roof. So there is an interplay between antiderivatives and areas. We come back here. Say this function has lots of antiderivative. Is that right? What's the antiderivative of 2x plus 2? Antiderivative of it what's the antiderivative of 2x plus 2? It's just a simple function. Antiderivative of 2x is just x squared. Antiderivative of 2 is just 2x. And you remember we always had that c hanging loose with any kind of these antiderivatives. The antiderivative of our roof is this. What does this have to do with the antiderivative? Let's consider this. You remember for antiderivative we used to use the capital F. This is that some antiderivative calculated at b, and this is that same antiderivative calculated at a. Now you might object that my antiderivative here was using some arbitrary constant c. This one is using a particular one, 3. But whatever constant you put here, it's going to cancel out. This minus 3 minus 3 makes these two constants cancel out. So it doesn't matter what constant I use. It's going to cancel out anyway. So this thing is equal to f of b minus f of a. Let's see if you understood what happened. This is a major thing. It's second piece of the theorem that's going to save your life over lots of calculations from now until end of the courses you are going to take in mathematics, and hopefully you continue using it when you are a scientist or an engineer or a mathematician. So very big idea here. We were trying to find the area between A and B underneath this roof. Go higher up. This was the roof. We were trying to find the area from A to B. It turned out that if I figure out the antiderivative of the roof and just plug the first and last point in it and subtract them, I'm going to get the area. Now you remember in the previous few lectures we had to go to hell and back to calculate the area. There was a long list of algebra to do to figure out the area from here to here, and you realize how big of an idea this is. It says you can bypass all that summation business and all that stuff you were doing there, provided that you figure out what's the antiderivative of the function that is playing the role of the roof. You take that function, you take the antiderivative of it, you plug the first and last point in it and subtract, and then you're going to get the area. So let's go ahead and write this thing down. Suppose f of x is an antiderivative of little f of x. What does this mean? It means if I take f and differentiate it, I'm going to get the little f. So that's the meaning of that. Don't get confused. Don't go in the opposite order. The derivative of capital F is little f. Then the area under f, that is little f, is going to play the role of the roof, under f over interval from a to b is f of b minus f of a. Now in the previous lecture we took about half an hour to calculate a certain area or a certain definite integral. And now we are going to do it in 1 minute. So let's go back to that exercise we had seen previously. Find integral. See if I can find it. Yes, it was, we were trying to find integral from 1 to 4 of x squared plus 2x minus 5 dx. Let's just keep using the interpretation of signed area for these definite integrals. So what does that mean? What did I just say? Just assume that here is some function. We don't need to be particular about it. So somewhere there, and it's 1, and then say it's 4 here, and here is your function f of x is equal to x squared plus 2x minus 5. We don't really need the picture. That's the beauty of it. We don't need anything. That's the area we want to find. That area is same as this definite integral. We use those two for each other. We don't care about the areas being negative or anything. It's fine. We are using signed area. So if it turns out something to be negative, that's not going to bother us. Okay, back to the problem. We are trying to find this area. So we have this function f of x is equal to x squared plus 2x minus 5. To answer, we need the antiderivative. It's a very simple problem to find the antiderivative. What's the function that if you differentiate, you are going to get x squared back? You remember we went through these things. It's quite easy. X cubed over 3. Let me use another color so that my background and foreground don't collide. Antiderivative of 2x. That's also easy. X squared. Antiderivative of minus 5, which is minus 5x. Our antiderivatives always come with some loose constant, some c. Okay. Go ahead and call this integral anything you want. Either call it an integral or call it an area, whatever you want to call it, that's fine. I just call it I. To calculate I, here is the recipe we arrived at. Take your antiderivative, plug the last point upper limit of your integration in it, and plug the lower limit in it, f of 1. So I just put 4 and 1 in it, put 4 and 1 in this, calculate, subtract, and then that's it. So I go ahead, I put 4 in this, 4 cubed over 3, that is 64 third plus 16, then I put 20, and our constant, and then I put 1 in this, so 1/3, and plus 1 minus 5 plus that constant. Right away we see that the constant is going to cancel out. It better cancel out because our area is just a number. It's not going to have any c's in it, so this constant better go away. How about the rest of the calculation? Well, in these problems, after a few examples, you get the knack of how to handle various kind of fractions in these things. Sometimes you get the benefit of fractions clearing each other out. So 64 minus 1 is 63 third. So I didn't go take a common denominator with these things. I hoped for a little bit of a mercy here. I just handle these two fractions first, and then I handle the rest of the numbers that I whole number. 16 minus 20, this is minus 1 plus 5. So it's better to lump the whole numbers together, fractions together, and hope that things get easier as you go down this. Well, that is 21 plus, now go ahead and do it however you want it. For example, you see 21 and this 21 cancel each other out. I have again a 16 plus 5, again another 21 shows up. Answer becomes 21. In the previous lecture, this answer took half an hour to get to it. It was rather cumbersome calculations to go through, and now you see this whole thing was done in one page. In fact, it can be done just on one line. The whole thing can be compressed into one line. Sometimes we abbreviate our writing in this style. So here's abbreviated solution. We're going to write it even in a more compact fashion. We have integral from, forget again, it was from 1 to 4 of x squared plus 2x minus 5 dx. On the right hand side, we go ahead and write the antiderivative. So I just write one antiderivative, x cubed third plus x squared minus 5x. We notice that the c didn't play any role at all. So we might as well skip writing the c's when we are doing definite integrals. Now, I was supposed to plug a 1 and a 4 in this. To indicate that, sometimes they put a bracket or a straight line, put a 1 underneath, 4 above. That is, you're copying these things that you saw here. The implication here, the meaning is that you are going to take these two numbers, plug it in this, and subtract. So that is our shorthand. So if we find the antiderivative, just copy the limits here, and then go ahead, plug this thing, like 4/3 over 5 plus 4 squared minus 5 times 4, and then subtract whatever you get by plugging 1 in this. I just wrote it out so that you see where things are going to land. Crucial thing is that you have to be careful about the subtraction. That's going to flip the signs inside. You have to be careful with that. We went through this subtraction here, so you do it and then you get an answer. If there is an exact answer possible, you first give the exact answer, and then you go ahead and use your calculator and perhaps convert it to decimal if it needs to be converted. But you always try to go for the exact answer the first time. Okay. That was the fundamental theorem of calculus and how it gets to be used. Let me go ahead and perhaps give a bit more explanation about why is it true? Okay, that's a big question. Why is the fundamental theorem of calculus true? Of course, it's a major help. Well, the full proof requires a little bit more rigorous math than what we have done, but we still can do can present the main idea. Let's go ahead and present the main idea here. We are done with however you want to use it, but we are coming to the foundation now. Why is this correct? Let's go ahead, take a function. Let's fix some starting point, and let's imagine that we have some ending point here. Let's call it x. So suppose a of x is the area up to x. That area, that's what is meant by a of x. What does the first part of fundamental theorem of calculus say? First part says a prime is just equal to f. So that's what we want to do. We want to prove this. And why is this thing true? That if you differentiate the area, you get the roof. Well, we have to go all the way back to what did it mean to differentiate. You remember what was the derivative? A prime of x from the very beginning of calculus 1 means you are taking the limit of a of x plus h minus a of x over h. So if you remember very first week of calculus, that's what we do over there. We learn about differentiation. Now the magic is doing this differentiation on this picture, understanding what this means on this picture. Well, we know what a of x means. This a of x that I see here, it means go as far as x and calculate the area. What does a of x plus h gonna mean? Well, that's gonna mean go as far as x plus h. What does that mean? X plus h means go a little bit further. Suppose this is x plus h. It's not a small h here, but I have to make my picture big so that you can see. So suppose we have come here to x plus h. Now what does it mean? So let's write out a of x plus h means area up to x plus h. If I take the area up to x plus h and from that subtract the area up to x, what am I going to get? Obviously I'm going to get the area from x to x plus h. So the numerator here is simply a of x plus h minus a of x, is the area from x to x plus h. Now what am I doing with that? I'm taking it and dividing it by h. Who is the h in my picture? H is this run. This is the h. After all, we said we are going from x to x plus h, so we traveled by h. Now if I take this area and divide it by this base, what do you think I'm going to get? Take this area of this strip divided by the base. Well, if it was a perfect rectangle and I divide it by h, I just get the height. It's just not quite a perfect rectangle. It has a little bit of a curve to it. But the ratio is going to be height somewhere between this low and a high. If I take this height, and this area, and divide by this base, I'm going to get the height somewhere. I don't know exactly where, but it's going to land somewhere inside this strip, perhaps the height here. Now what comes to rescue is that we are taking the limit. If I squeeze these two sides toward each other, at the limit, where does this blue line have to go? Well, it's going to coincide with those two. All three of them are coincide on top of each other. In that case, how tall is it going to be? It's going to be exactly as tall as the height of the function as at f of x, the height of this black line. So a of x plus h minus a of x over h is equal to height of the roof f of x at some point in the interval from x to x plus h. There's a theorem that proves this thing, but we are just relying on intuition. I divide this area by this base, I'm going to get the height somewhere. Next we say as the limit is taken, that means as h goes toward 0, all these three lines, the whole region collapses on top of this black line. This height becomes the height at x, which is just f of x. So a prime is in fact equal to f of x. Okay, so that's the fundamental theorem of calculus. You go ahead and apply it to also the problems that you are going to see in this section, and it would be a very good exercise for you to try to do as many of these exercises as possible. They are all routine, and you just need to build your knowledge by these exercises. I guess I better stop here. Good luck and God bless.